Here in this work, I will talk about facial expressions. Facial expressions are a way of nonverbal communication. One person can communicate with another with making this facial expression. And what we can communicate with them is our emotional state. Here are some examples of what Paul Ekman called the basic emotions and the related facial expressions. It is very intuitive for us humans to interpret these facial expressions. We all know that the person with the facial expression in the first picture is happy only by seeing his face. And some interesting fact is that computers are also good at classifying facial expressions. But as any form of communication, facial expressions can be lies. This means that we are also able to fake a happy face even if we are sad. Like the previous problem of identifying a facial expression, the problem of detecting a fake facial expression is something very difficult both from humans and from computers. So, what we are trying to do here is train a computer to identify fake facial expressions. This work started in 2017 with a challenge from ICPRS conference where we participated. In that challenge, a dataset of videos with high space and time resolution was presented. It is interesting to make a comment on how the dataset was built. Participants were asked to act two facial expressions of emotion in a sequence, a genuine one and an untitled one. These two emotions were based on their differences. After each genuine facial expression of emotion, participants were asked to display the opposite. Participants were not aware of the fact that they would be asked to display a second facial expression. The challenge was followed by a paper that proposed a machine learning system that used microexpressions information to perform a classification. So here is the dataset of the challenge. They considered these 6 emotions. They recorded 2 videos of each emotion, one real and one fake, and that was for each subject. Training dataset had 40 subjects for a total of 480 videos. Each video had a label for the subject ID, a label for the kind of expression, and a label for true or fake. The validation dataset was released at the same time, but only with the expression label. For the final phase of the challenge, they released the true-fake label of each validation video. At the same time, they released the test dataset, again only with the expression label. The true-fake labels for these videos were never released. We conducted many experiments, and all of them had the same scheme. We'd first train a neural network to acquire some pertinent attributes for each frame of each video. That network is called Attribute Generators Net. We then represent each video with a matrix when each row corresponds to a frame of the video. We feed a second neural network with it. This second network is called Classifier Net. These are the attribute generator nets. The first one is a convolutional neural network trained to predict identity. The next 3 are also convolutional networks trained with different datasets to predict kind of emotion. This one is a feed-forward that uses landmarks as input. And this last one is the combination of these 2. These are the classifier nets. We first try with 2 feed-forwards, one deeper than the other, and then 3 recurrent networks. The first one uses the raw data. The second one uses the difference from the previous frame, and the third one gets its input as 1, -1, or 0, depending on if the value is higher, lower, or equal. We also experimented with the amount of epochs of training and the amount of frames taken for the video. Here we have all combinations among all models and parameters trained with the training dataset and evaluated with the validation dataset. Each column shows a different classifier network. Each row shows the amount of frames extracted from each video, where 0 means that all frames were used. In simple sight, we can appreciate that the 3 recurrent are slightly better than the 2 feed forward, but nothing conclusive here. When we separate by kind of expression, we see better results. Here we can see that some achieve 90% of accuracy. So we came up with this idea. We can choose the best combination for each expression. Then we should get an accuracy of 90% more or less. But we have one problem. The problem is we use the validation dataset to choose the best combination for each expression. And the test dataset is not labeled, so we can't use it. Finally, we decide to divide the validation dataset and use 1/2 of validation to choose the best model for each expression and the other half as testing. So, after we did this, which one is better? Here we got another problem. The validation dataset was too small, so measuring only accuracy is not useful. We have a lot of ties. So we need a new metric to untie. Let's take a look at this example. These two networks, A and B, classifies instance I as true, because both of them returns a higher level on perceptron true. This phi indicates the level of the network confidence for a class and an instance. But the first one can be considered better because of the difference between the true level and the fake level. The second one also returns true, but is very close to choosing fake instead. So we define the trust level of a network, giving higher values to networks that have better confidence on their results. And we run the experiments again. Now we have more information to untie. This should give us a perfect classifier, but running the experiments, well, this was the result. Maybe it was because of the low amount of data, or maybe because the attributes need to detect FX expressions that are relative to each subject. The thing is, we couldn't generalize. But we have here some interesting results. When we rank the better combinations for expression, we notice some patterns. For example, except for the very first, most of the better combinations were from recurrent neural networks. Here, you also see some patterns. For example, happiness and surprise seems to be very related. Well, we saw that recurrent networks in this case were slightly better than deep feed-forward networks. Maybe it was because of the low amount of data, but our model couldn't generalize enough for any subset. Also, results didn't suggest that sampling more frames of the video achieves a higher accuracy.